Hello, this is Gary LaRue, Technical Editor at the Microwave Journal. It's my pleasure to welcome you to today's webinar with John Coonrod of Rogers Corporation. He will be discussing design considerations and trade-offs for microstrip, coplanar, and stripline structures designed for millimeter wave frequencies. Before we begin John's presentation, let me cover a few items so you know what to expect. The webinar will last an hour. After John's presentation, we'll have some time for questions, which you may submit at any time during the hour. Just type your question into the Q&A panel that you'll find on the right-hand side of the WebEx screen. And please address the question to all panelists, which is the default setting. That way, all of us will be able to see it. Shortly after the webinar concludes, you'll receive a copy of the slides via email. We are also recording today's presentation, so you may watch it on demand and recommend it to colleagues who are not able to watch it today. The recorded version will be available in the events section of the Microwave Journal website within about 24 hours. Now let me introduce our speaker. John Coonrod is a technical marketing manager for the Advanced Connectivity Solutions business at Rogers Corporation. John has been involved with the PCB industry for over 28 years. Initially, he was responsible for circuit design, applications, processing, and materials engineering. He has since supported the high-frequency, rigid PCB materials made by Rogers, including electrical characterization studies, circuit fabrication, and application support. So he's well-versed in today's topic. John is also the vice chair of the IPC D24C High-Frequency Task Group, and he received a bachelor's degree in electrical engineering from Arizona State University. John, I'll turn the screen over to you now.
Okay, thank you very much. Welcome, everyone. And I'm going to be talking today about considerations and trade-offs for three different structures used in millimeter wave frequencies, which is microstrip, coplanar, and stripline. The coplanar, I'm always going to be referring to as grounded coplanar, but as you'll see, I'll talk about some other coplanar a little bit as well. So what I plan on doing, give me a second for my, there we go, get my slides indexed. So what I plan on doing is shown here, the agenda. First off, I'm going to go through some pretty basic transmission line theory, and I think most people on this webinar are pretty familiar with it. So I'm going to buzz through this topic pretty quick, to be honest. And then when I get to the point of some of the millimeter wave concerns, I'm going to slow down and spend a little more time there. And then the rest of the presentation, I am going to get in a fair amount of details. So the basic structure, looking at microstrip, coplanar, stripline, and then after that, we'll look at some comparisons of these different structures across a pretty wide range of frequencies. And then also, finally, we would end up talking about some of the variables due to printed circuit board fabrication and how that can affect RF performance. So to begin with, some basic transmission line theory. Again, I'm going to buzz through several of these slides pretty quick because I think most people online here probably are aware of this already. But as you all know, microwave and millimeter wave engineers typically refer to waves a lot and wave properties. Wavelength is a pretty big deal. A lot of times we're looking at fractions, half wavelength, quarter wavelength, and basically wavelength is the physical length of the wave from one point to another point on the same wave. And a low frequency is basically a long wavelength, and a short wavelength is high frequency. And there's different kind of waves that could be resonant on a PCB transmission line, and TEM wave or quasi-TEM wave are usually waves that are desired. And TEM stands for transverse electromagnetic wave, and that's where the electric fields perpendicular to magnetic fields, which are perpendicular to the wave propagation. And again, usually TEM or quasi-TEM, which is kind of a modified TEM, those are the waves that you usually want on a PCB transmission line. There's other waves too, so TE wave and TM waves, those are possible. On some cases, actually hybrids. But anyway, as I said, the TEM or quasi-TEM is usually what's desired, and sometimes you run into scenarios, which we'll talk about, where you have moding problems. And what that means is there's some other wave propagation modes that can interfere with the desired mode. So the desired mode being TEM or quasi-TEM. These TE or TM waves or other waves can actually interfere with what you want and cause problems. So this moding or mode suppression we'll talk about later on. That's a pretty big deal in millimeter wave, actually. Then properties, I'm not going to spend much time on this. Basically, I'm going to call relative permittivity DK, which is not a good term, actually, but it's one of those things I just got used to, and most people in our industry call it DK, dielectric constant. The proper term, I think, is relative permittivity, and that's also noted as epsilon sub r sometimes. But most of the materials used in the printed circuit board industry have a DK in the range of about 2 to 10. There are some exceptions. We have a few materials outside of that range. And then for relative permeability, or basically the property that affects magnetic fields, most of the printed circuit board materials used in the industry have a mu sub r, relative permeability of 1, which basically means the material is not magnetic or not ferromagnetic, or it doesn't affect the magnetic fields. My animation didn't work very well, so you're going to have to use your imagination here. But really what I was trying to show is a circuit with a low dielectric constant has a shorter wavelength and a faster wave propagation, and a circuit, the exact same circuit, with a higher dielectric constant material would have shorter wavelength and slower wave propagation. So conductivity, copper is used as the conductor on most printed circuit boards, and copper is one heck of a good conductor. A lot of times what happens is in the PCB fabrication process, a metal finish is added to the copper for various reasons, and most of those metal finishes are less conductive than copper, and they cause more conductor losses. And I should not use the word all there. I apologize for that. It really should be most, because there is an exception, and we'll get into that. And then basically what happens is with the metals with lower conductivity, it's going to cause more conductor losses, and it most certainly can affect the skin depth as well. And then some general typical diagrams of transmission lines and how they work. Really, a transmission line is connecting things together, and it could be a lot of stuff, wires, cables. And on a printed circuit board, usually a transmission line is just a simple structure that connects two modules, in most cases for RF printed circuit boards. And there's losses associated with the transmission line, of course. And here I've given a very generic, simple example. It's basically saying the transmission line is losing 3 dB of insertion power or loss. But anyway, 3 dB actually turns out to be half the power. So 3 dB may not look like a big number here, but actually it's a big deal. So 3 dB, that number is actually pretty magical to a lot of RF designers because it really is a half power level. And then S parameters, S stands for scattering. There's a lot of different ways to look at wave and RF performance on a printed circuit board, but S parameters are actually a nice, easy way of thinking about these things. And one way to think about it is if you think of port 1 as the input, port 2 as the output, the insertion loss or the total loss of the circuit is really S21, and the meaning of S21 is that's the scattering parameter of the energy received at port 2 that came out of port 1. So that's the S21 nomenclature, I suppose. And then S11 is return loss, and that's basically how much energy was received in port 1 that came out of port 1. Basically, how much energy came out of port 1 was reflected right back into the port. And you can go the opposite direction. You can say the same thing about S22, how much energy came out of port 2 reflected back in, or S12, which is insertion loss, that is really power received at port 1 that came out of port 2. Typically, I report S21 just as a matter of habit, I suppose. And here's an insertion loss curve where I measured S21 on two different circuits that were identical in every way except for length, and then I subtracted the difference. Using the exact same impedance connectors, I'm kind of subtracting out the effects of the connectors when I do this, leaving units in dB per inch in this case. Excuse me. So this is a Microstrip transmission line. It was based on a substrate that's 5 millR 3003 laminates, going from about 10 megahertz out to 110 gigahertz, which is as wide as band as I can measure. And it's actually pretty well behaved. And well behaved usually for me is thinking that you have 15 dB return loss or better out to about 50 or 60 gigahertz. And after 60 gigahertz, I'm usually pretty happy if I have about 12 dB loss when you get into the higher frequencies. So insertion loss is made up of 4 different components. There is conductor loss, dielectric loss, radiation loss, and leakage loss. I'm not going to talk much about leakage loss, mainly because most of the printed circuit board materials used in the industry has high volume resistivity, which means you usually don't have an issue with leakage loss. There are some exceptions. Some high power applications you can see exceptions. I'm not going to really talk about that today. Radiation loss we're definitely going to talk about because that can be an issue at millimeter wave. Dielectric loss and conductor loss, definitely going to talk about both of those. So here's a slide that I actually present a lot of times when I talk about insertion loss, because it's a nice visual way to think about how insertion loss is made of different components and how these different components can actually dominate or not dominate certain factors. So what I did was make 3 different sets of circuits on the exact same material. It's all using an RO4350B laminate. And the only difference really is thickness. And in the effort to maintain 50 ohms, I have different signal conductor widths to maintain 50 ohms. And to start off with the chart in the middle that's got the legend, that's using 10 mil thick microstrip transmission line 50 ohms, and the thick purple curve is the measured data that I got. And that's going out to about 20 gigahertz, and y-axis is loss in dB per inch. And then the other curves are a model from our MWI 2017 software that's free for download from our tech support hub. And the green curve is the total loss, which should match the measured loss. And for what we're doing today, that's pretty good. That's pretty close. But what's nice about this model is it breaks out what makes up that total loss. So it shows you how much dielectric loss is associated with it and how much conductor loss is associated with it. And the red curve is conductor loss. And in the case of the 10 mil thick circuit, the middle chart, there's more conductor loss than dielectric loss that makes up the total loss. And then when you move to the left and look at the same type of curves there, what you find, the curve on the left, the curves on the left are based on a thinner circuit. So this is 6.6 mil thick. And one thing to note there is overall there's definitely more insertion loss, and that's what happens when you go to a thinner circuit. And in this case, the reason that happened is because there's more conductor losses. So in general, a thinner circuit is going to be more sensitive to conductor effects. And in this case, we're talking losses. So a thinner circuit is going to be more sensitive to the conductor loss and whatever changes conductor loss. And then on the opposite end of the spectrum, far right chart, that is looking at the same material again, except now it's thick, 30 mils thick. And here you can see the red curve, the conductor losses are not the dominant factor on a thick circuit. It's actually the dielectric losses are. So if you had an issue with a thick circuit like on the right and you wanted to actually have less losses, what you'd probably want to do is change from 4350B materials and maybe go to RO3003 materials, which has lower dissipation factor, because that's going to affect the blue curve, the dielectric losses. And if you did go from a rough copper to a smooth copper, which we know does minimize the conductor losses, if you did that on a thick circuit like the chart on the right, you're really not going to get much bang for the buck, so to speak. But if you do that on the chart on the far left on a thin circuit and you go from a rough copper to a smooth copper surface, which will decrease the conductor losses, then that red curve will come up some and you will definitely improve the overall insertion loss. So long story made short, a thinner circuit is much more sensitive to conductor effects, conductor loss. A thicker circuit's more affected by dielectric losses. Then there's radiation losses. Radiation losses are rather difficult to accurately capture, I think, and they are dependent for several things. So frequency dependent, higher frequency, more radiation loss, circuit thickness dependent or substrate thickness dependent. The thicker the substrate, the more radiation loss, and then dielectric constant. A higher dielectric constant means lower radiation loss, or the opposite, lower dielectric constant, higher radiation loss. And then there's circuit design issues. And as a general statement, microstrip transmission lines are more prone to radiation than grounded coplanar. And then strip line, if it's designed correctly, can have no radiation. Signal launch is the transition from the connector to the printed circuit board, and that transition can definitely have issues with radiation. Spurious wave mode propagation, basically interfering waves, that can also cause some radiation. And then impedance transition and discontinuities. Many times these impedance transition and discontinuities are purposely put there for design reasons. And if these are not designed correctly, you can also have radiation associated with those. And then this is some more charts, pretty much what I showed a couple of slides ago, but now including radiation losses. The chart on the left is the 10 mil thick RO4350B. And I've included radiation losses, and you can see on a 10 mil thick circuit at low frequencies, there's really no radiation losses. And even when you get out to 20 gigahertz, there's still not a significant amount. But when you look at the chart on the right that's got the thicker circuit, there you can see the radiation losses, again, at very low frequency, 1 or 2 gigahertz, not a big deal. When you get out around 10 or more gigahertz, then the radiation losses really kick in and start to be a dominant factor. And this is one of the reasons why thinner circuits are used as you go to higher frequency, and that is to avoid radiation loss. And also thinner circuits are used to avoid these spurious wave modes that can interfere with the wave you do want. And the one drawback to that is thinner circuits will have more insertion loss. That's just kind of the nature of the beast. So some spurious wave mode things. Let's talk about that real quick. And this is kind of a funny topic, and I'm going to approach it in a kind of a practical way, but if you get into much details, it can get pretty complex. So there's a couple of different ways to think about this. One is if the distance between the signal plane and the ground plane, basically the substrate thickness, if that happens to be, let's say, a half wavelength, then you're going to set up a good resonance between the signal plane and the ground plane, and that resonance is going to generate a lot of energy, and it's going to interfere with the wave that you do want, the quasi-TEM wave. And that's one issue. Another issue, which is actually more common, is the conductor width. So you can actually have a standing wave set up across one edge to edge of the width of the conductor. If that happens to be a half wavelength or a quarter wavelength, you can set up these resonances, and these resonances can generate their own wave that would interfere with the wave that you do want. The wave you do want is usually a TEM wave or a quasi-TEM wave, and I found from several different experiments that making sure that these features are 1/8 wavelength or less is a good thing. So you do not want to have circuit features, thickness, or conductor widths that are larger than an 1/8 wavelength. I think academically we usually say a quarter wavelength, but actually just from a practical sense, I've seen that you can have issues even a little bit bigger than 1/8 wavelength. And just kind of going down this path a little bit farther, and also making a couple of points in these charts, is that I'm looking at the same material with rough and smooth copper, and this is the RO4350B is the blue curve, and that's the standard copper, which is high profile, and it's relatively rough. And just to make sure I'm clear on things, the copper roughness I'm talking about, that surface is really the interface between the substrate and the copper as we make the laminate. So anyway, the blue curve is the standard 4350B materials, high-profile copper, rough copper, and the purple magenta curve, whatever color that is, that has lower insertion loss, that's actually used in our RO4350B low pro, which is a low profile or smoother copper. And you can see on the thin circuit, upper left-hand chart, there's a pretty big difference in insertion loss out at 50 gigahertz, that the smoother copper definitely has less losses, and that's a good thing. But also, as you look at these charts going to the right, that's a little bit thicker, about 6.6 mils thick, bottom left 10 mils thick, bottom right 16.6 mil thick. And you can see as you go thicker, the benefit of going from rough copper to smooth copper is less. So again, thinner circuits are more dominated by conductor effects. So going from rough copper to smooth copper on the upper left-hand chart, you can see a pretty good benefit there. Another thing I wanted to point out in these charts is the insertion loss curves. And you can see the thin circuit, upper left, has insertion loss curves that's actually pretty smooth. Looks like they're pretty well behaved. And then when you go to the right, 6.6 mil thick, out at higher frequencies, around 40 to 50 gigahertz, you see that there's a little bit of noise in the insertion loss curves. Bottom left chart's thicker again, 10 mil thick. You see more noise at higher frequencies. And then finally, the bottom right, 16.6 mil thick, you see a lot of noise out around 40 to 50 gigahertz. And that's really because as you go thicker, you're getting more of these spurious wave modes that are interfering with your quasi-TEM mode that you want. And a good way to look at this is a chart that I've shown here on the thickest of our example, and that's the 16.6 mil 4350B and low pro. And if you look at the conductor width, in this case, it's 36 mils, 0.036 inches. And out at a quarter wavelength, or where that dimension is a quarter wavelength in frequency, you see there's a bunch of noise out there. So out around 44, 45, 46 gigahertz, there's a lot of noise out there. If you look at the insertion loss curves going from 10 megahertz up to about 24 gigahertz or so, those insertion loss curves are pretty well behaved, and that's in the range where the conductor width is less than an 1/8 wavelength. So in general, 1/8 wavelength or less is a good thing for avoiding some of these various modes. Signal launch is the transition between the connector and the printed circuit board. And in my example here in the next few slides, I'm going to be talking about a microstrip transmission line where there is a signal conductor on top, ground plane on the bottom. And really we're looking at the transition from a coaxial type of connector to a circuit. And the printed circuit board is actually a parallel plate structure. So one of the problems that you can have with signal launch, actually there's multiple, and I just made a short list here, there's several. One is at lower frequencies, signal launch is a little bit less of an issue. As you go to higher frequencies, signal launch becomes definitely more of an issue. But one thing is in this transition area from the connector to the printed circuit board, really you have electric fields transitioning orientations. So in the coaxial connector, the electric fields are a cylindrical orientation, and in the printed circuit board, they're planar. So that transition is one issue, why signal launch can be problematic. And then also another is the wave propagation mode is a little different. So the coaxial is a pure TEM wave, usually. And then if you're going on to a microstrip, like our example is, that's going to be a quasi-TEM wave, and that means the phase velocity is actually going to vary with frequency. However, the pure TEM wave, the phase velocity is really not going to vary with frequency. So I've given an example here to kind of visually show this. And if you look at the phase velocity of a 2.4 millimeter coaxial cable, and also a microstrip transmission line, 50 ohms based on 30 mil thick RO4350B laminates. And if you normalize this at 2 gigahertz, you can look at phase velocity in the y-axis and then frequency on the x-axis. And you can see that the phase velocity for the 2.4 millimeter coaxial cable with the pure TEM wave is unaffected with frequency. It's pretty much constant. And then the phase velocity with the microstrip transmission line, where it's a quasi-TEM, because the fields are used in both air and substrate, and the fields react different in air and substrate as frequency changes, then you can see that there is a difference. And that difference regarding signal launch can be a pretty big deal. And now at about 50 gigahertz or so, with the 30 mil thick transmission line, there's about 0.97 difference of phase velocity between the coaxial connector and cable and the circuit. However, if you go and use the same material and make a 10 mil thick much thinner, you actually improve the situation a lot. And now the phase velocity is only 0.97, so that's a big improvement. It's getting closer to the coaxial, which is what you want. If you even go thinner, that's improved more. Now, if you go the other way, the 25 mil thick RT Duroid 6010.2 LM, that's the correct wording for this material, and I made a mistake there in typo. But anyway, that material is at a high dielectric constant, about 10.2. And if you looked at the normalized phase velocity for that at 50 gigahertz, that's even worse. That's about 0.87 at 50 gigahertz. And that really is a more of a problem. So higher dielectric constant is typically more problematic for signal launch, and thicker circuits more problematic for signal launch, and higher frequency more problematic for signal launch. So let's look at some of these structures real quick. First off, there's microstrip, and I've shown a cross-sectional view of a microstrip transmission line in the upper right, and there's a signal conductor on top, ground plane at the bottom, so a 2 copper layer circuit. The nice thing about this transmission line, it's pretty cheap to make, it's pretty good reliability, easy to assemble because you get the signal conductor right there exposed. And this is actually one of the most common transmission lines in the industry right now. A lot of times it's not a standalone circuit like I'm showing here. A lot of times it's actually part of a multilayer, and it's the top copper layers of a multilayer. The dominant wave propagation mode, which is basically the wave mode this circuit wants to have, so to speak, is a quasi-TEM wave. And also there's something called an effective decay. And the reason it's not a pure TEM mode and the decay is an effective decay is because the fields, electric fields and the magnetic fields associated with the structure are using both air and substrate. And as you go across a range of frequencies, the fields actually react different in air than the substrate, and that actually changes the phase velocity as well. And because of that, you get a wave that's not a pure TEM wave or not a pure plane wave. It's a quasi-TEM wave. And also you get more dispersion, or basically the wave is going to behave different as you change frequencies. So for some losses, microstrip circuit dielectric losses are mostly related to the dissipation factor of the material itself. And then also if you put solder mask over the signal plane, the solder mask is actually going to increase the dielectric losses. Conductor losses, there's actually a pretty long list of things that go on there, and I kept it simple. One is skin effect, and as we all know, when you go to higher frequency, you have thinner skin depth, which means you're using less of the conductor to support the current. Using less of the conductor means more conductor losses. And then there's surface roughness, and the copper surface roughness comes into play when the skin depth is equal to or less than the copper surface roughness. Then the copper surface roughness has an impact on conductor losses, and it also has an impact on phase response. and also final plated finishes. So as I mentioned already, some of these final plated finished metals are less conductive and cause more conductor losses, and we'll talk about that more later as well. We have a paper on this topic, and at the end of the presentation I give some references, and we show that a rougher copper compared to a smoother copper, the rougher copper does cause more conductor losses. Also, a rougher copper compared to smooth copper, the rougher copper will slow the phase velocity, and even though the substrate could be exactly the same, when you compare a rough copper and smooth copper, the circuit with the rough copper is going to have a reported higher dielectric constant value because the wave slowed down, and a slower wave means higher dielectric constant. So a rougher copper can affect the phase response and can affect the conductor loss. Radiation losses. At lower microwave frequencies, usually not a problem. Mid to higher microwave frequencies, a millimeter wave, radiation losses can be a major issue. And that's basically how much energy is radiated off of the circuit. Microstrip is more susceptible to radiation losses than other RF structures. It is frequency dependent, and I think we already talked about these dependencies. So higher frequency, more radiation loss. Substrate thickness, the thicker it is, more radiation loss. And also the dielectric constant, the higher it is, less radiation loss. And the reason why higher dielectric constant has less radiation losses is because higher dielectric constant will cause the fields to condense. And now the fields are more condensed inside the substrate, so to speak, and they're less likely to radiate off. So grounded coplanar waveguide. So when I talk about coplanar, I normally mean grounded coplanar waveguide. That's the structure in the upper right-hand corner as a cross-sectional view. That's the structure that's used most often in microwave and millimeter wave engineering. There are other coplanar structures. Middle right picture is a conventional coplanar waveguide, and then bottom right is edge-coupled conventional coplanar waveguide. And these are usually not used in microwave and millimeter wave. There are definitely exceptions, though, and they can be used. But mostly what I see is the grounded coplanar waveguide, and also called a conductor-backed coplanar waveguide, or CCPW. Now, the vias that connect the coplanar ground planes to the bottom ground plane, those vias are pretty important. Also, how they're located is pretty important, and I'll talk about that, I think, in a couple of slides. So on this slide, just talking a little bit more about the grounded coplanar waveguide structure, and it does have an effective decay like microstrip, and it's for the same reason that the fields are used in both air and substrate. It also has dispersion, as microstrip does, but if the grounded coplanar waveguide is designed correctly, you can get this designed to where there's much, much less dispersion with the grounded coplanar waveguide as compared to microstrip. Same comment with radiation losses. If the grounded coplanar waveguide is designed correctly, there will definitely be less radiation losses than microstrip. And the same with dispersion. So bottom line is a lot of times engineers will transition from a microstrip transmission line to a grounded coplanar waveguide transmission line when they transition from like microwave frequencies to millimeter wave frequencies, because there's definitely some benefits to grounded coplanar waveguide. There are some drawbacks, as you'll see when I get into the printed circuit board fabrication influences. But in general, grounded coplanar waveguide is going to perform better at millimeter wave frequencies than microstrip. The dominant mode for this structure is quasi-TEM, kind of like microstrip, and suppressing these spurious wave modes that can interfere with what you really want. That's a lot easier to do with grounded coplanar waveguide than it is microstrip. And then signal launch issues, the transition from the connector to the circuit, that's also much easier to deal with and more effective when you're using a grounded coplanar waveguide structure as opposed to microstrip. So here's a simple drawing of some fields for grounded coplanar waveguide. These are electric fields only, and the drawing is okay, but the location of these vias is not okay. The location of those vias actually should be moved closer to the ground signal ground interface, and I'll talk about that on the next slide, I think. But basically, the losses associated with insertion loss for a grounded coplanar waveguide, dielectric losses, that's mostly due to the dissipation factor of the substrate. And then if you do put solder mask on top of this structure, what you'll find is the solder mask will increase the dielectric losses, and actually it's going to increase dielectric losses a lot more than it will microstrip because of the coupling structure between the signal plane and the neighboring ground planes of the coplanar layer. So the coupling is actually using the dissipation factor of the solder mask whereas without solder mask, it's using air and substrate, and some substrate too. Conductor losses, same type of issues that you have in Microstrip, but as a general comment, the structure of a grounded coplanar waveguide, and here I've put GCPW, that's the same thing, just a different terminology. That's conductor-backed coplanar waveguide. Same thing, just different terminology. But anyway, the conductor losses associated with the grounded coplanar waveguide are definitely more than Microstrip just by the nature of the structure. And then conductor losses due to final plating finishes are definitely worse with grounded coplanar waveguide as compared to Microstrip. And I'll talk about that a little later as well. Radiation losses, if the structure is designed correctly, you can have minimal or almost no radiation losses with grounded coplanar waveguide as compared to Microstrip, where you are going to have some amount of radiation losses probably. And then the via placement. The via placement in the grounded coplanar waveguide is pretty important. And ideally, what you'd like to have is these grounding vias from the coplanar ground plane to the ground plane below. You'd like to have those vias adjacent to the edge of that ground plane on the top copper layer, but because of printed circuit board fabrication tolerances, you really can't do that. There's got to be some kind of gap there. And just comparing the circuit on the left to the circuit on the right, the circuit on the right is actually going to have a little better performance because it's closer to that edge. And what happens is with the circuit on the left that has more of a lip, I guess, if you want to call it that, that added copper actually adds to the parasitic parallel plate inductances and increases the impedance and actually increases the conductor loss some. And the circuit on the right is going to be a little better performance type of circuit. Also, if you look at these vias and how they are located in the length axis, not shown here, basically going into the screen, from one via to another on that axis, the pitch should be eighth wavelength or less. If it's around quarter wavelength or more, you can get resonances and you can have some bad things happen. So eighth wavelength or less for the pitch along the length axis is a good thing. Stripline structure. Give me just a second to take a sip on my coffee. Okay, stripline structure. It's a 3 copper layer circuit, 3 metal layer circuit, ground signal ground. And it's probably the second most common structure that I see in the industry, and it's a very wide band structure, so you can use this across an extremely wide range of frequencies. It's a little bit more complicated to fabricate than like a Microstrip or a grounded coplanar waveguide just because you got more materials and you have to have some bonding materials to glue things together and all that kind of fun stuff. Anyway, the substrate, if the substrate that makes up the strip line has all the same properties, then you can get a true TEM wave on a strip line circuit and actually have very little dispersion or no dispersion. And if designed correctly, you can have no radiation loss at all. Some of the different structures are a balanced strip line, and that's normally what I see. Bottom left corner is a a microsection picture of a balanced strip line where the signal conductor is in the geometric center of the structure. And then to the right on the bottom is an unbalanced strip line where the signal conductor is much closer to the bottom ground plane than the top ground plane. That's a little more unusual, but I do see that from time to time. And then continuing on with the losses on strip line, dielectric losses are mostly due to the dissipation factor. In fact, I'd have to say all due to that. It does get a little complicated, though, because you have sometimes more than one kind of material on a strip line where you have layers of material that need to glue the layers together, the pre-preg or bonding materials. And sometimes the pre-preg and the cores have different properties, so it's possible to have different dissipation factor, which would make up kind of a composite dissipation factor. And then also along those same lines is if you have materials of different dielectric constant, then you may not get a pure TEM wave out of this. You could get a quasi because of the difference of the dielectric constant of the different materials. And then conductor losses, similar to what we already talked about, where skin effects are coming into play, and also copper surface roughness. The effects of the copper surface roughness is a little more difficult to deal with the stripline circuit because now you have 4 of these copper substrate interfaces, and each of those interfaces have different things going on. And in a lot of times, as the circuit is made, we may know what the copper surface roughness is on 2 of those layers, but just by the way the circuit's made, we may not know the copper roughness on the other 2 layers. So copper surface roughness is a little more tricky to understand for the strip line structure. And then as a very general statement, if you can compare a strip line 50 ohm circuit using the exact same material, same thickness of material, same everything, to a microstrip and a grounded coplanar waveguide, normally what you see is the strip line structure is going to have overall more insertion loss than these other structures. It depends on a lot of things, actually, but that's kind of a general statement. So continuing on strip line structure, the placement of these vias that connect the top ground plane to the bottom ground plane are pretty important. And one of them is that eighth wavelength should still apply, so the pitch along the length axis, not shown here, that's going into the monitor, so to speak, the pitch from one plated through hole to another on the length axis should be eighth wavelength or less of the highest operating frequency, and also how close you want to get that via to the signal if you don't want it to couple to it is about 3 times the width of the signal conductor as a general rule of thumb, so to speak. And then the big issue on this structure is actually signal launch, trying to get the energy from the outside world into that buried signal conductor. That's usually the big trick. And that signal launch via typically has an increase in inductance, but it could be capacitance. It could be a variety of things, actually, when you get in the details. And the signal launch via itself can actually act as a stub in a certain area and radiate and cause reflections and forward return loss. I'll give an example of that here in just a second. And then also the design of the signal via sometimes has what I would call a stepped impedance characteristic. And again, I'll talk about that on the next slide. So this slide is showing a multi-layer circuit, and layers 3, 4, 5 are the strip line circuit where it's ground signal ground. You have a vertically mounted connector in gray on top, and that's actually using air in the connector. So what you have is, if you think about the signal flow going down the connector pin and onto the circuit, in the area of the connector you have dielectric of air, and then once you meet the circuit, now you have this boundary of air going to substrate. So that's one mismatch, so to speak. And then also the circuit itself, in this case, looks like it's got a coplanar at that launch, which is sometimes used to help deal with reflections and different things. But anyway, it could be a difference in impedance right at that junction. And then as you go down a little bit from the copper and in the middle of the layers between copper layer 1 and copper layer 2, the impedance is actually going to go higher. And then once you get down to copper layer 2, where it's looks like a coplanar type of structure, the impedance is going to go low. As you go down a little bit deeper between layer 2 and layer 3, impedance goes high again, then low again, high again, low again. So you get this impedance transitioning low, high, low, high, low, high, and that can cause some problems at millimeter wave. But sometimes it's purposely done because the via itself could be inductive if it's a smaller diameter than the pin of the connector. And if you put in these different coplanar areas, that adds to the capacitance and tries to offset the inductance. And sometimes that's a good thing. Now, another thing that is done often is this extra length of the signal via really is not serving any good use, because you want the signal to go down the connector, down the via to layer 4, basically, the signal layer, and then transition out the page at U. And the rest of the energy, you don't want to go down this the rest of the via. And that rest of the via can act like a stub and can radiate energy, can cause reflections, can do bad things. So a lot of times the fabricator would drill that out with a controlled depth process, and they call it back drilling. And generally at low frequencies, that's really not necessary, not that big a deal. Higher frequencies where this starts to radiate and cause other problems, that can be a big deal to do that and very beneficial. So let's now talk about some structure comparisons. Here I'm going to talk about microstrip versus grounded coplanar waveguide, and I'm showing in red the current density. This is just approximate. That's just to kind of give you the thought process. And you can see that the current density on the microstrip circuit on the top cross-sectional view, that current density is used on a lot of the surface that is roughened. So between the substrate and copper, that surface is the rough copper surface. And on microstrip, you can see the ground plane uses a large area of that and the signal plane as well. But on the grounded coplanar waveguide, the circuit below, you see that the coupling between the coplanar sidewalls, there's a fair amount of energy there. And now the ground plane below, the lower ground plane, has less of the rough and copper being used, basically. So bottom line is when you change from a rough copper to a smooth copper on microstrip, you do see a pretty big benefit because of the smoother copper and the roughness being used so much for a microstrip. And then in the case of the grounded coplanar waveguide below, if you go from rough copper to smooth copper, you still see a benefit, but not as much as a microstrip. And also, it depends on how tightly coupled or loosely coupled. If the grounded coplanar waveguide on the bottom picture is loosely coupled and there's a big gap between the signal and the adjacent ground conductors in the coplanar layer, then you do get more current density on the bottom layer, and you are using more of the roughened copper. So it kind of depends on how tightly and loosely coupled that grounded coplanar waveguide is. Here's an example of tightly and loosely coupled grounded coplanar waveguides. My nomenclature is tightly coupled as W18S6, and what that means is the signal conductor is 18 mils wide, and the space between the signal conductor and the adjacent grounds is 6 mil. So a pretty tight space, tightly coupled. Loosely coupled, W21S12, 21 mil wide conductor and 12 mil wide space. And if you look at the differences in insertion loss, what you'll find is the tightly coupled W18S6, when you look at copper roughness of 2.3 going to 2.9, going from smooth to rough, the difference in insertion loss is 0.82 dB, and the unit should be dB per inch. So on the tightly coupled, there's a difference of 0.82 dB per inch, and looking at this difference in copper roughness. On the loosely coupled, W21S12, the difference between that same copper roughness, 2.3 and 2.9 microns RMS, there's more difference, 0.131 dB per inch difference. So basically it's showing that a loosely coupled grounded coplanar waveguide is more sensitive to the conductor effects and the change in surface roughness. Here is some comparisons of the three different structures: Microstrip, grounded coplanar waveguide, and Stripline, all using the same material. The material is 5 mil RO3003 laminate with the standard ED copper. And the most lossy structure in this case is the Stripline. It is a balanced Stripline structure. The grounded coplanar waveguide is considered moderately coupled, and that's a conductor of 12 mils wide, space of 7. And then the Microstrip is a straight Microstrip transmission line, except in the area of signal launch. So what I did was I used in-launch connectors for the signal launch, and just in the in-launch connector area only, I had a grounded coplanar waveguide. And I did that to help the signal launch, and it makes a big difference. So it is a microstrip circuit in the body of the circuit, but right at the connector signal launch, it's a grounded coplanar waveguide. So there you can see some differences of the three different structures using the exact same material, out to about 50 gigahertz. Now, this is a nice chart showing a big difference in copper roughness. The last couple of slides back, I showed differences of 2.3 versus 2.9, but this is a much bigger difference. This is rolled copper with the copper surface roughness about 0.35 microns RMS compared to the ED copper about 2.0 microns RMS. And by the way, RMS is also R sub Q for copper surface roughness measurements. So this substrate's used at 77 gigahertz a lot, and at around 77 gigahertz, you can see there is a big difference between the insertion loss curves, where the rolled copper is the gray curve and the blue curve is using ED copper, again, the exact same material, 5 mil RO3003, and at 77 gigahertz, there's about a 1 dB difference, and that is considered a very large difference and very beneficial to use rolled copper. Now, rolled copper also has less variation in surface roughness from batch to batch. So copper foil that we buy coming into us, it does have normal copper surface roughness variation. That's just the nature of it. And the rolled copper, it's just so smooth to begin with, the variation is very little because the surface roughness is so smooth to begin with. The ED copper, a little bit rougher, it is going to have more variation, and how that can be an effect and actually an influence is actually when you're looking at phase angle. And a lot of this material is used at 77 gigahertz for automotive radar, and radar is very sensitive to phase angle. And in this case, what I showed was the difference of unwrapped phase angle. So basically, this is phase angle across frequency that's just accumulated. So unwrapped phase angle at 77 gigahertz between the circuit using ED copper and the circuit using rolled copper, I see a difference of 61 degrees for phase angle, and that's pretty significant. So if you are interested in using these different coppers, you need to make sure you understand that there is a phase angle difference just due to the copper surface roughness. And essentially, a rougher copper is going to slow the wave down for phase velocity, and it is going to change the phase angle as well. So some printed circuit board fabrication issues. This charts, both these tables of information are something really interesting, I think, because I've had customers come to me before and say, you know, we have this controlled impedance board, it's about 50 ohms, and we see this variation, and we want to use a tighter controlled material for dielectric constant. And actually, when you do the models, that's not what you really need that much. I mean, it would help, of course, but that's not the big thing. And anyone can actually take a impedance modeling software and do this exact same model. And to begin with, the top table of information is using a material with dielectric constant of 3.5, and the tolerance is plus or minus 0.05. And then the substrate thickness is 20 mils thick. The total copper thickness is 2 mils thick. And what I mean by that is the substrate started off with a half-ounce copper, and then the fabricator plated up the copper thickness for the process of putting in plated through holes. But overall, the entire copper thickness on the final circuit is 2 mils thick. Then the conductor width I set at 43 mils, and I get an impedance pretty close to 50 ohms. That's my baseline as the first raw information. And then what I did was change the substrate thickness by 10%, and I looked at the difference in impedance, and then I put the model back to the baseline, and then I changed only the dielectric constant by 0.05 lower, looked at impedance, and then copper thickness changed from 2 mils to 1 mil, looked at impedance, and then finally looked at a different conductor width. And what I find was the hierarchy of the most significant influences shown at the bottom here, where the most significant influence is the substrate thickness. Next would be the conductor width. Next, copper thickness, and dielectric constant variation is actually the least of the problems. And then if you do that same type of model and thought process on a thinner circuit, make it 10 mils thick, and repeat the whole thing, what you get is the exact same list of variables in that same order. So it's the same influences, except now the magnitude of the differences are more. So when you change the thickness, the impedance change is much greater, copper thickness change much greater, and all that stuff. So the bottom line is, at millimeter wave frequencies, typically thinner circuits are used for several reasons. And if that's true, you need to be mindful that the substrate thickness is now even more important, and also the conductor width and the copper plating thickness is also more important. Some of the applications we deal with at 77 gigahertz for automotive sensors, they're using 5 mil thick substrates with 3 dielectric constant. That's our RO3003 materials. So I did a model on that. In this case, I'm doing the same type of thing I did on the last chart, except now I'm looking at phase angle response. And in doing so, I find that there's a different hierarchy of variables and how they influence things. So 3 dielectric constant, 5 mil thick circuit, 2 mils thick of copper, 11 mil wide conductor, gets me about 50 ohms. And actually what I'm looking at is the phase angle, shooting for 180 degrees by using a line segment that's about 49 mils long or so. And that's my reference. Then I do the same thing as I did on the previous charts, and that is I change the thickness by 10% and see how much the phase angle changes. Then I change the dielectric constant, look at the phase angle, copper thickness change, phase angle. You get the idea. So anyway, in this case, what's most important is actually the copper thickness. And that copper thickness is not just the thickness as we make the laminate. That's the copper thickness of as we make the laminate, the raw copper itself, and also the circuit fabrication that does plate out copper on top of our copper, and that variation is something you probably should be pretty mindful of. As you can see, that's the top dog here. That's the most important. Next in line is dielectric constant variation. So here, dielectric constant variation is a big deal. Having a material that's tightly controlled, that's really important. Conductor width is next, and substrate thickness is the least of your worries if you're just looking at phase angle differences only. So at higher millimeter wave frequencies, or millimeter wave frequencies, 77 gigahertz, typically thinner circuits are used, and phase angle for some of these applications is really important. If that's true, you want to keep these things in mind. So now some other things I ran into. This is a study I did a while ago where I'm looking at grounded coplanar waveguide, tightly coupled and loosely coupled, and I'm looking at the difference in copper plating thickness. And I did this purposely because I ran into several issues along this line. And what I did to try to minimize the materials effects as much as I could is I used the same sheet of material to build all these circuits. I started off with a 24 by 18 sheet of material, which was on 10 mil RO4350B laminate. The 24 by 18 was cut in half, and half of that sheet, which is now 12 by 18, was used to make circuits with thin copper plating, and the other half of that main sheet turns out to be 12 by 18, of course, and that was used to make thicker copper circuits. So the exact same circuit design, same everything, just one half of the panel was used to make circuits very thin copper plating, and the actual copper plating of the circuit ended up being 1 mil thick overall, and then the thicker copper-plated circuits ended up being 3 mils thick. So this is a pretty good difference in copper plating thickness. And it does make a difference in insertion loss and in phase angle response. So what I did was take measurements of the insertion loss measurement, and across the range of frequencies that I'm showing here, 66 to 68 gigahertz, the reason I picked that range of frequencies, one is I wanted to show millimeter wave responses, so I wanted to get in that range of frequencies. Two is I wanted to make sure all sets of circuits had good return loss. So in this range of frequencies, all sets of circuits had very good return loss, and in that range of frequencies, I usually think of 15 dB or better for return loss being good. Actually, these were all up around 17 or even a little better, so these were really good. So I would say very well-behaved circuits. And what happened is kind of what you would think intuitively, and that is the circuits with the wider conductor is going to have lower conductor losses and lower loss, which it does. And then also the circuits with taller copper, thicker copper, the sidewalls between the ground signal ground and the coplanar layer, these sidewalls are now taller, so you have better use of the air, so to speak. And now you have more fields in the air. Air is the lowest loss medium, so the lowest loss circuit should be W21S12 thick copper. W21, the widest conductor, and thick copper. On the opposite end of the spectrum, W18S6 thin copper. So that's the most narrow conductor, 18, and also has the thinnest copper, which means there's less coupling on the coplanar layer and more coupling within the substrate, so less coupling in air. Then I did the same thing looking at the effective dielectric constant of the coplanar circuit, and what I did was use the phase response formula, and I manipulated it to use two different circuits of different lengths, and that's the delta L. Actually, in this case, I was using 8-inch long and 2-inch long circuits. Everything's identical with these circuits except for the physical length. And then I measured the phase angle of each one of them. That's S21 phase angle, delta phi, at a specific frequency, and that's how I get the effective dielectric constant. And I did this over a wide range of frequencies, again, looking at millimeter wave, and my thought was, if this is tightly coupled, let's say the upper, or the picture on the top picture, on the bottom right picture, the top picture, if it's actually thick copper and tightly coupled, that means you're using air very effectively. The fields are using air very effectively, and air is the lowest dielectric constant, so that's going to have the lower effective dielectric constant. And then in the case of the loosely coupled, where the fields are not coupled as tightly in air and probably coupling more down in the substrate, then you're going to have a higher effective dielectric constant. And here shows the results. And what's interesting, it did pretty much what I thought. So the W21S12, this is the widest space, so it's loosely coupled and thin copper. So it's not making as good use of the air, so to speak. And it's the highest effective dielectric constant. The circuits with the lowest effective dielectric constant were tightly coupled, 6 mil space, S6, and very tall walls between the ground signal ground. So you are making good use of the air. So electric fields are coupled in air quite well, and air is low for dielectric constant. Now what's interesting is this is using the exact same material. Like I said before, I just cut the sheet in half and made circuits. And you can see I got a difference of 0.3 in the effective dielectric constant when using the exact same material. That's a pretty significant difference. And for millimeter wave, this is something you should be mindful of. So grounded coplanar waveguide has a lot of advantages in millimeter wave, but the copper plating thickness can be problematic. I just have a few more minutes, so I might speed up a little bit. I don't have too many more slides. So I want to talk about final plated finishes. This is really pretty important. Most of the final plated finishes, most of the metals used, are not as conductive as copper, and because of that, you get more conductor losses. The one exception would be silver, and the silver process used in printed circuit boards is called immersion silver, and that applies silver really, really thin. So the benefit of silver and having better conductivity is usually not realized until you get to really high frequencies where the skin depth is really thin. Now, sometimes people ask me, why is this metal finish adding to the conductor losses in the case of microstrip? Because most of the fields are between the signal plane and the ground plane. Well, if you do electromagnetic modeling, you'll find right at the edges of the corners here, there's always a high current density on both of the edges. And in that area, that is being affected by the final plated finish. In this case, we'll assume ENIG, electrous nickel immersion gold. And at those corners, you're going to have much higher conductor losses due to ENIG. And it's also an accumulative effect, where if it's a short circuit, not much difference. Long circuit, these losses add up to cause more problems. And it's at the edges here. But in the case of the grounded coplanar waveguide, normally with the same lossy plated finish, you will definitely have more losses on a grounded coplanar waveguide than a microstrip. And the reason why is because now you got 4 edges using this lossy metal that are coupled together. Now, there's also a thickness dependency with these metal-plated finishes, and as I said before, a thinner circuit is more sensitive to conductor differences than a thicker circuit. In this case, I'm using the same material, RL4003C, and the 20 mil thick circuit comparison between bare copper and ENIG is the blue versus the red curve. There's a difference about 0.21. That's the thicker circuit. Using the same material but thinner, 8 mil thick, the difference between bare copper and ENIG causing more losses. The difference in the thinner circuit, 0.38 dB per inch difference. So it shows that a thinner circuit definitely has more conductor losses and reacts to these conductor differences much more than a thicker circuit. Here is an output of one of the studies I did years ago. Unfortunately, at the time, I had not figured out signal lengths very well at millimeter wave range, so beyond about 42 or 44 gigahertz, the return loss is not too good. So this is kind of a good general thing to look at for trends. But if you truncate this down in the range of frequencies where it was well-behaved for return loss, then 10 megahertz to 40 gigahertz, you can see pretty clear differences here. The reference is the light blue curve, which is the bare copper circuits. And you can see that those three circuits have pretty much behaved the same, and that is the bare copper circuits, immersion silver, and OSP. Basically saying immersion silver and OSP are the same. They're really not causing any more losses. Solder mask is causing more losses, but it's really dielectric losses. And then these other metals are causing conductor losses. Immersion tin is used a lot at 77 gigahertz, NEPIG, and ENIG is also used. ENIG is always more lossy than any of them, and that's because nickel is about one-third the conductivity of copper. And then this is something interesting, not really related to millimeter wave, but I thought I'd just show it real quick, that these different metals actually do affect the phase response. So I'm showing dielectric constant as reported by the circuits through phase measurements. And at lower frequencies, these composite conductivity made up of copper, nickel, gold for ENIG actually will change the phase response. And some of the problem there is nickel will change in thickness from one circuit to another, and the change in nickel thickness will actually cause that phase response to go up and down from one circuit to another. Now, out of millimeter wave frequencies, what we're mostly talking about, you get to a thin enough skin depth where that's really not an issue, but I thought I'd kind of throw it out as a FYI. And at the very end here, I have some references that gives you a little more information, and I'd like to leave you with inviting you to become a member of our Tech Support Hub. Got a lot of good information in there. We're real proud of it. We got some videos that are instructional, a lot of papers, some presentation and trade shows, some software that's free, and different things like that. And I think I've got a few minutes for questions, but I ate up most of the time, I think.
Well, John, you did cover a lot of material in a very detailed and informative presentation. I wish I had had this presentation when I was first starting to do microstrip design. It would have saved me a lot of time and agony. Let's take a couple minutes at least for some questions, because we do have a lot of them that came in. One that should be fairly simple and may help quite a few folks. One of our viewers says, in some Rogers materials, such as your 4350B, there are actually two D sub Ks mentioned in the data sheet, a process spec and a design spec. Which one should someone use if they're designing a millimeter wave antenna?
Yeah, the process dielectric constant is as we make the material and we're controlling our process. The design decay is really what should be used. And that goes back to what I said back here somewhere, where the copper surface roughness affects the phase response. And a rougher copper will slow it down, a smoother copper may have a little faster, and that slower or faster phase response relates to how the circuit perceives the dielectric constant. So that's what the design decay is trying to account for. So the design decay on the data sheet is a generic number, and if you want more information, either contact us or download our MWI 2017 software that shows the design decay as frequency dependent, thickness dependent, copper roughness, all that stuff. So design decay is really what you should use.
Okay, good. Another question, the grounded coplanar waveguide and stripline look better for high-frequency range performance compared to microstrip, but the viewer says, what about higher sensitivity to accumulated manufacturing and material accuracy tolerances?
Yeah, there's a good question, too. Because stripline, you have the issue of bonding things together, and that bond line can vary in thickness, so that's one issue. Stripline also has the issue that the circuit fabricator has the choice sometimes of what kind of copper they want to put on there. So if they put a rough copper or a smooth copper on there, that can make a difference for how the circuit behaves in phase response and loss. So there's a bunch of different things to consider. I think as a general statement, Microstrip has less variables that the circuit fabricator can mess with, so to speak. So usually Microstrip has less variables that circuit fabrication can alter. And grounded coplanar waveguide, a little more sensitive to the copper plating thickness and strip line thickness differences. That's kind of a quick overview of that, I guess.
Okay. Another question related to rule of thumb for line spacing. This viewer has seen n times the substrate width or n times the trace width. Which would you recommend?
Say that again. I didn't catch all that. That's for an impedance, like 50 ohms that you're shooting for?
I think it's line spacing, maybe for Microstrip. Does it relate to the some multiple of the substrate width or some multiple of the trace width in terms of parallel lines?
Oh, that's a pretty good question. I hate to say it depends, but it does depend. So if you have a high dielectric constant material, then the coupling is different between the lines and than a lower dielectric constant material. And personally, I would go with a substrate thickness relationship myself. But,
okay.
Man, that really does depend on the dielectric constant because that really can alter the coupling a lot.
Is that something with current EM modeling software that someone could actually do a simulation?
Yeah, actually, our software we have on our website, MWI 2017, can do Microstrip edge coupled, and it's relatively accurate. But, yeah, a lot of the electromagnetic modeling softwares can do that. And also, I guess a quick note on our MWI 2017 software, I really tell people that's kind of a ballpark tool, so it's a quick reference to look at things real quick, and then when you think you got what you want, then jump over to Field Solver or something a little more accurate.
Okay. Let's see if we can squeeze another one in here. You talked about the quasi-TEM mode in Microstrip because you have the air above and the substrate below. This viewer asks, what would happen if we placed a dispersive material instead of air over the Microstrip structure? Have people done that before to try to mitigate any quasi-TEM performance degradation?
Yeah, that's interesting. I guess that's a good question, actually. So if you put solder mask on top of the signal plane, of course, that's going to do something different. And if it was matched to the same decay as a substrate, I think that's going to cause it to be less quasi and more like a TEM wave. But to be honest with you,
more like strip line, maybe.
Yeah, exactly. But to be honest with you, I really haven't dabbled with that. In theory, it seems like you could do things like that to make it less dispersive. I just haven't tried it. I'm not too sure. It seems fine theoretically.
All right. And the last question I'll squeeze in here, have you ever tried gold plating without the nickel layer?
Yeah, actually years ago when I was doing flex circuit design, we had a fabricator that was interested in not having nickel really for mechanical reasons, that if you try to flex a circuit, nickel's very brittle and it breaks real easy. So gold is more ductile and you can actually flex a circuit that way. And what they found was there's actually some diffusion formulas you can use that will predict over time and how much temperature it's operating at, how long you have before the copper oxides migrate through the gold and make the gold really ugly and bad. So if you have a service time of like a year or something like that for your circuit, then you could plate enough gold over the copper to where in that time frame the gold's going to stay good. But it's just a matter of time before the gold's going to go bad with the copper oxides migrating through the gold.
So it becomes a reliability issue.
Yeah, it does. And if you plate the gold thick enough, then it's just a battle over time more than anything else. And also temperature. If it's a hot application, then these oxides are going to grow through the gold even faster. But if it's thick enough gold, it lasts longer. So that's that kind of thing.
Mm-hmm. Well, unfortunately, we're out of time for more questions. For those of you who did not get your question answered, certainly refer you to the Rogers website and some of the resources that John has suggested. And we're also providing a list of all the questions to John and the team. So, John, thank you very much for the very detailed and informative presentation, and we want to thank Rogers Corporation for making it available. A reminder that the webinar has been recorded. It will be available for replay, and you'll find it in the events section of the Microwave Journal website, and it will be posted in about 24 hours. So if you want to watch it again, because a lot of material was covered in a short period of time, you can do that. And feel free to recommend it to colleagues who would also benefit from watching it. And within the next few minutes, you will receive an email, and you can, from the email, have a link to download John's presentation slides. There's a lot of good material there. So thanks, everyone, for joining us today.